In this episode, the US Navy's fastest combat ships.
If you're a pirate or you're a drug runner and you see that ship coming towards you, it's time to shut down your engines and put up your hands.
Marine engineering in a class of its own.
She's basically one of a kind as far as warship goes. I am sailing a ship that's unprecedented.
And the pioneering historic innovations.
Here we go. Yes.
If these engines were to cut out, this boat would be in serious trouble.
Whoa! This is really incredible. What an amazing airplane.
That made the impossible possible. The US Navy is the largest sea force on the planet. Throughout its 242-year history, its ships have carried out operations in the deep blue waters of the world's oceans. Now, the assignments are evolving.
The world is changing, and so too must our Navy to adapt to it. Gone are the days of open water Blue Navy battles. Many of the places where we need to be as a Navy are in coastal regions.
To combat problems such as piracy, people trafficking and aid distribution, the fleet must operate in shallow coastal waters, known as the littorals. And as shipbuilding program manager Captain Tom Anderson knows, this requires a particular kind of vessel.
To operate effectively in the littorals, we need a high-speed ship, and it's got to be adaptable. It's got to be capable of doing multiple missions. That's our challenge.
A challenge that Chief Engineer Lieutenant Damon Gilbert is also familiar with.
The ideal ship for this environment would be a ship that's light, a ship that has a very shallow draft, and a ship that can handle itself and move very quickly.
The solution: the Littoral Combat Ship class. Made up of the monohull Freedom variant and the trimaran Independence variant, this new class of ship represents the vanguard of marine engineering.
This is the face of shipbuilding in 2017. This design, whether it's the monohull design or the trimaran design, this is going to change the face of how we operate inside those waters for years to come.
Built for speed, both the Freedom variant's semi-planing hull and the Independence variant's trimaran design create ultra-hydrodynamic efficiency. Using lightweight aluminium powered by an innovative propulsion system, each ship can travel in excess of 40 knots in little more than 4 meters of water. Designed to be reconfigured for multiple missions and deploy smaller boats, a vast helicopter pad extends the crew's reach. To produce a high-performance fleet for shallow waters, Littoral Combat Ships designers faced a series of complex engineering challenges. Perhaps none more difficult than finding the most effective propulsion system.
So to make a traditional propeller system work, the propeller blades need to sit below the hull so they get the proper flow, which would add to our draft.
Not only do standard propeller systems increase how far the ship extends below the waterline, they're relatively slow to react.
In the littoral waters, if you want to chase down a ship or you want to elude another vessel to get out of danger, you want to be able to maneuver as quickly as possible.
So how do you propel a ship at speed in swimming pool depths? This would not have been possible without a genius innovation from the past. Humans have always needed to navigate the world's shallow waterways. First off, we used arm power to paddle. Effective but tiring.
Out the way.
The Vikings added a sail to conquer the coastlines. All well and good,
Huh?
as long as there was wind.
Oh, for Odin's sake.
With its small draft, the paddle steamer seemed to be the answer.
Well, I do declare, Vikings.
But they weren't without their problems.
Oh, my.
In the 1940s, the introduction of airboats brought high-speed travel to the Everglades.
Whee! Oh, no.
Luckily, a better system was round the corner.
Show off.
The Grand Canyon is one of the natural wonders of the world, but it's also the site of one of history's great engineering achievements.
Woo! Here we go.
Mechanical engineer Dan Littoral is taking a white-knuckle ride on the Colorado River to find out more.
Oh, this is brilliant. The beautiful noise you hear right now is two 550 horsepower, 8.3 liter engines pushing this 20-ton boat up these crazy, crazy rapids. If these engines were to cut out, this boat would be in serious, serious trouble.
But the secret to driving against the flow of these powerful rapids isn't down to the mighty engines, but a special propulsion system.
Getting to places where others can't in extremely shallow water was born out of the imagination of someone's childhood desire was to challenge the rapids and go where no one else could.
To do this, New Zealand-born inventor William Hamilton needed to overcome the limitations of standard motorboats.
So the problem with conventional boats is that as the boat moves through the water, traditionally it's powered by a screwed propeller. Now Hamilton had a problem with this because the waters he wanted to go on were too shallow. Huge rocks would effectively wreck the screwed propeller.
Hamilton's solution was to do away with the propeller altogether. In 1954, he commissioned a plywood boat, attaching a centrifugal pump to its engine, creating a unique water-driven jet propulsion system.
How the Hamilton jet motor functions is, around the middle of the boat, there's an intake that brings water in from whatever body of water the vessel is navigating. Hamilton uses an impeller that's spinning very fast to greatly accelerate this stream of water. That water is highly turbulent and twisty, and so the Hamilton passes the water through a series of stator vanes, creating a uniform but high velocity jet, creating the massive thrust, allowing this boat to travel at such high speed.
The powerful jet of water coming from the stern propelled the boat forward with equal velocity. Hamilton tested his designs on the New Zealand waterways, and in 1960 set his sights on the Grand Canyon in the USA.
Hamilton vowed to be the first to take a vessel up a 160-kilometer section of this notoriously unnavigable Colorado River. Now, it may look calm right here, but upriver, the rapids are crazy.
Traveling against the current, including the notorious Vulcan Rapids, in just 9 days, with son John at the helm, he had made history, conquering the mighty river. Almost 60 years later, Hamilton's water jet's sheer power
Acceleration is intense.
and the ability to navigate shallow waters with the added benefit of mind-blowing maneuverability
Here we go. Yes!
continues to open up new waters.
Thanks to this spectacular demonstration of man versus rapids, that this unique propulsion system was embraced across the planet. All right, let's go.
LCS engineers on both the monohull and trimaran variant have taken Hamilton's water jet innovation and used it to create a propulsion system of unparalleled performance.
Ship has a requirement to do 40 knots. 40 knots is a very high speed for a ship of this size. The way that this ship achieves that speed is through the use of 2 gas turbines and 2 diesel engines that drive a propulsion train that is propelled by water jets.
At Austal USA's shipyard in Mobile, Alabama, the latest Independence variant USS Tulsa is having her jets inspected, ready for launch.
When this ship is going full power, there's roughly 24,000 gallons per second passing through these 4 water jets, which equates to the ability to fill 2 Olympic-sized swimming pools in less than a minute.
Not only do they generate colossal power, these cleverly engineered jets act as a rudder to steer the ship.
Each water jet is capable of independently being steered, which allows for a lot of flexibility and maneuverability.
Like Hamilton's system, water is ducted through 4 mighty impellers and discharged at high velocity astern. To steer, each jet's water flow is deflected by a rotating nozzle, enabling fast, agile maneuvers. And to reverse, the exit nozzles force the jet flow backwards. Built into the hull, the LCS can operate in just over 4 meters of water.
300 yards turn. Next course 309.
As sister ship, the USS Montgomery patrols the Californian coast, Commander Mark Stefanik is making the most of the ship's assets.
The water jet system allows me to turn and maneuver the ship with much more fidelity and a great deal more responsiveness than a traditional ship. So by creating opposite forces on either side of the ship, I can actually turn the ship almost on its own axis. I can twist the ship in a perfect circle because of the amount of control I have through the water jets.
Behind the ship, the 100,000 horsepower propulsion system forms an impressive wake.
This is actually our full capacity right now. As you can tell, there's quite a bit of turbulence back there, so we're pretty mindful of what we do with this wake. If we can make sharp turns, we can easily knock over small boats.
The vessel's ability to stop is equally impressive.
When I pull the ship to stern and go from full speed to 0, it's a very, very smooth transition. The entire ship just basically will stop in the water within less than a minute.
By using water jet propulsion at 29 horsepower per ton, compared to an aircraft carrier's 3 horsepower per ton, the Littoral combat ships are the most efficient in the Navy. The ship's incredible capabilities aren't lost on the USS Montgomery's crew.
When it comes to the maneuverability of the ship, it's unlike any other ship out there. It's basically like driving a jet ski. This ship could actually maneuver sideways. It could pivot itself by standing still. That's something totally different from any other warship out there.
Its propulsion system is unrivaled, but to be a truly trailblazing addition to the US Navy's fleet, its designers face more challenges, and will have to turn to innovations from the past.
This is a special type of awesome to be flying this amazing aircraft. Cannot describe to you what this is like.
To produce more impossible engineering. The Littoral combat ships are the quickest and most agile in the US Navy. Program Manager Captain Tom Anderson believes their performance is unsurpassed.
If you're a pirate or you're a drug runner and you see that ship coming towards you, it's time to shut down your engines and put up your hands.
Built for multiple missions, the trimaran Independence variant and the monohull Freedom variant are engineered to patrol the planet's coastlines, known as the Littorals. But to operate fully loaded at speed, without running aground in these shallow waters, the ships must be as light as possible.
Every pound that goes into the ship is assessed, because every pound that goes into the ship is an increase in its draft and a decrease in its speed.
For Lieutenant Damon Gilbert, USS Freedom's chief engineer, solving this problem is crucial.
The difficulty we find with the older ship designs is the steel hull with the steel superstructure makes the ship incredibly heavy. The less weight we have going into the Littorals equals a smaller draft. Smaller draft equals a longer sustainability inside those Littorals without worrying about running aground, without worrying about getting into situations that we can't come back out of.
So, how do you build a lightweight combat ship without compromising on strength or size? To find a solution, littoral combat ship designers need inspiration from another genius innovator of the past. Man has always strived to find the perfect material to stay afloat. For Tamil fishermen, a log under each arm was all that was needed.
Come here.
Although being mainly submerged was a bit of a catch. In the 9th century BC, Assyrian soldiers would lie on inflated goat skins to sneak up on their enemy.
Uh-oh.
Although lightweight, they weren't without their problems.
Hello? And push.
For some, clay was a cheap alternative. A row of pots could buoy a raft with great effect.
Steady. Look out. No.
Although avoiding the rocks was always advisable. Luckily, a more durable material was on its way. Engineer Dan Dickrell is in Tulsa, Oklahoma, unveiling a game-changing marvel that sparked an aviation revolution.
Oh, wow. What a beautiful airplane. Such an engineering icon. This is the DC-3 flagship Detroit. She was constructed 80 years ago, made almost entirely of aluminum. It's the oldest flying DC-3 in the world. But this engineering and aviation marvel would not have been possible had it not been for the work of an engineer 3 decades prior to her construction.
Prior to this stunning machine, most planes were made of wood. Although lightweight, it was easy to break. In 1931, a Fokker F-10 lost an entire wing and crashed into the Kansas prairie, killing all 8 people on board. As America reeled, wood frame construction ceased, and engineers turned to metal. But it wasn't until 1906, when German metallurgist Alfred Wilm made a chance discovery, that metal planes became a real possibility.
The problem with constructing airplanes out of metal is, well, metal is stronger than wood. It's also much heavier. Now, with metals, different metals also have different weights between them. Here we have aluminum, and here we have steel. For the same size, steel weighs about 3 times as much. Because of aluminum's relative lightweight, it seems like the ideal material to construct aircraft from. The problem was 100 years ago, it just wasn't strong enough.
In the late 19th century, mass-produced aluminium was relatively weak. Alfred Wilm began experimenting with its chemical makeup to find a solution.
He introduced different metals, manganese, magnesium, and copper, in different ratios to create an alloy. He heated it to high temperatures and then quenched it. He repeated this process over and over again. Unfortunately, the aluminum was still very bendable.
Wilm gave up, but on his return to the lab a few days later, something extraordinary had happened.
The aluminum had age-hardened. It was much, much stronger.
The aluminium's soft crystals had been altered by the introduction of the metals. Over time, new, minute crystals had grown within each one of the aluminium crystals, reinforcing its structure.
Wilm called this new material duralumin. It was very strong and quite literally changed the face of aviation.
The new alloy became known as the winged metal. 80 years after its construction, this iconic all-aluminium DC-3 is taking to the skies once more.
This is amazing. Take it down just a little bit.
For Dan, taking the controls of this groundbreaking aeroplane is the flight of a lifetime.
This is a special type of awesome to be flying this amazing aircraft. Cannot describe to you what this is like. I'm flying the world's oldest DC-3.
First launched in 1935, the lightweight DC-3s were the world's first commercially successful passenger planes.
Using Wilm's alloying recipe, the aluminum in this DC-3 has an amazing strength-to-weight ratio. It's lightweight and aerodynamically efficient.
With this new generation of safe and efficient aircraft, by 1939, more than 90% of America's passengers were flying on all-aluminium DC-2s and DC-3s.
Today, 80 years after the launch of this aircraft, aluminum is the standard material in the aerospace industry.
Taking inspiration from aerospace, LCS Freedom variant engineers have used high-grade aluminium to create some of the lightest combat ships of this size ever built.
One of the design elements that was put into this particular design of LCS was a bimetallic hull, meaning the actual hull itself is steel, where the superstructure, or what we like to call sometimes the house where people live and where all the facilities are, is actually comprised of aluminum, thus saving literally tons of weight, which has a direct effect on the draft.
In spite of the Freedom variant's 118-meter length and 17.5-meter width, with its steel hull and aluminium superstructure, it weighs a mere 3,500 tons, with a draft of just above 4 meters. Engineers on the Independence variant, however, have gone one step further.
So the L in LCS doesn't stand for little. We're building a sizable ship here. As you can see, as you take a look at the stern of the ship, this ship is the largest all-aluminum vessel operating on the seas today.
Constructing these trimaran megaships in Austell, USA's Alabama shipyard, at 127 meters long and a colossal 31 meters wide, every kilo counts.
Aluminum has great strength-to-weight ratio. It's a third of the density of steel. And for the volume of ship we're building here, aluminum structure was the only way for us to meet our speed, range, and draft requirements. So as we take a look inside the ship, you get a feel for the structural members and the construction, including the external sheathing, is all aluminum.
And taking Alfred Wilm's approach, adjusting the recipe, Their marine-grade aluminium has one remarkable quality.
Aluminum alloys that we use in construction of this ship have good corrosive properties, which means, unlike other Navy ships where exposed steel needs to be painted, this ship is not painted above the waterline. That saves us money, and it also reduces the weight of the ship.
And that huge weight reduction means the Independence variant's draft has been dramatically reduced to just over 4 meters.
Normally, we would have about twice the draft that this ship has. And that enables us to go into waters and visit ports that traditionally our Navy ships have not been able to get into.
It's a pretty incredible feat of engineering in order to get a ship this size to have a draft of only 14 feet but still be able to maintain maneuverability in deeper waters.
The Littoral combat ship designers are pushing the boundaries of marine engineering. But to effectively carry out multiple missions, they must draw on further innovations from the past.
Here I am aboard the ray gun. This can manage speeds of up to 28 miles an hour.
To produce more impossible engineering. The US Navy's cutting-edge littoral combat ships are taking marine engineering to new heights. Built to patrol coastal waters for Program Manager Captain Tom Anderson, the LCS is a standout class.
Operating in the shallows require high-speed ships with shallow drafts. The answer to those challenges is the Littoral combat ship.
Made up of the monohulled Freedom variant and the trimaran Independence variant, the LCS's power-to-weight ratio is more than double that of a typical destroyer. But as USS Independence Commander Douglas Mayer knows, 21st century challenges require these ships to offer more than speed.
Ships today have to do several different missions well. The environment that we live in today is forever changing. It's very important for a ship to have the ability to adapt quickly to the changing threats.
We need to have a ship that's capable of doing multiple missions, whether it's searching for submarines, finding minefields, and detonating those mines. All these things are required for the future Navy.
And to be truly adaptable, not only must these ships carry equipment for multiple assignments, but also have an effective platform for air-based missions.
When we're conducting helicopter operations, there are limitations as far as how much pitch and roll a ship can have based on the weather and environments in order to conduct those helicopter operations.
So how do you marry the performance of a speedboat with the volume and stability of an aircraft carrier? To solve this seemingly impossible problem, the US Navy's designers would need more inspiration from the past. Off the south coast of England, science communicator Kate Mulcahy is discovering the origins of some of the fastest, most stable sailing vessels ever built.
Here I am aboard the ray gun. This is a 24-foot boat that can still manage speeds of up to 28 miles an hour. And the reason for that is its incredible design. It has not one, but 3 hulls that are designed to cut through the water to provide minimum resistance. While this class of boat is one of the fastest in the world, up until the 1940s, it didn't exist in the racing world.
In 1946, Ukrainian engineer Viktor Chechet unveiled this trailblazing shape at Marblehead Race Week in the US, calling it a trimaran. And proving his prototype design, he beat most conventional boats, winning second prize overall. Although revolutionary in the yacht racing world, his design was inspired by Pacific Islanders, thousands of years previously looking to improve the performance and stability of the humble canoe.
Unfortunately, we're not here in the Pacific. I'm actually in a very rainy creek in Cornwall. But nonetheless, you can still see why this design has endured for so many years. It's thin and long, which means it moves easily through the water. Also, it doesn't have a keel, so it sits quite high in the water. That means it's perfect for exploring shallow, narrow waterways like we see here. Despite all of this, the design does have some problems. Firstly, it can only go as fast as I or anyone can paddle in it, which means its speed is limited. Secondly, as you can see, it's not very stable. So imagine this out on the open water contending against waves. So if I was to try and get it, I try and, I don't even think it would be possible without it capsizing. So not ideal.
Islanders' canoes performed well in calm coastal waters, but island hopping in the open ocean was practically impossible. A new design was needed.
And what they came up with was this. This is the same long, thin central hull, but with two outriggers lashed parallel on either side. Now, when we were making this, we've used plastic tubing, but they would have been using just logs. Now, hopefully this may add stability, but the only way we're going to know is to take it out in the water and test it.
By adding either one or two outriggers, the performance of the simple canoe was instantly transformed.
So you can see this boat is much more stable. It's practically impossible to capsize it. The addition of the outriggers has increased the stability and also increased the buoyancy. That means that it sits higher up in the water and means it's easier to explore the shallow. And finally, allowed me to add a sail, so no more paddling for me.
With this ingenious design, islanders could now paddle and sail across open water and access islands throughout the Pacific Ocean. And decades later, Chet-Chet's modernized trimaran is still inspiring some of the most successful yachts on the planet.
Improving on the ideas of the islanders, Chet-Chet used the wide, stable base to create a greater spread of sail. He also streamlined the light, buoyant hulls so they cut through the water and created minimal drag. All of this is what makes the trimaran, it's one of the fastest class of sailing boat in the world today.
Littoral combat ship engineers have taken the principles behind Chet-Chet's racing yacht and created the Navy's first high-performance trimaran combat ship. At Austell, USA's shipyard in Alabama, the USS Tulsa is receiving its finishing touches.
You can see I have very fine-tuned bow designed to pierce waves. As we go further back, you see the hull widen. And just here to the right, you can see the outrigger. And again, just like those canoes, with the outriggers, which give us that added stability, we get high speed.
The stabilized central hull with two outriggers moves the ship's displacement point upwards, reducing drag, allowing it to reach speeds of over 40 knots. Not only is it fast, it's adaptable. Its wide beam allows a 1,050 square meter flight deck and can accommodate smaller vessels below ready for launch, extending the ship's capabilities across the world's oceans.
Trimarans are stable platforms, and those are really important when you're doing things like operating helicopters, launching vehicles and conducting high-speed maneuvers when you're doing surface warfare type events.
At sea level, the unique engineering is clear.
You get a really good perspective of just how wide the ship is and how that trimaran design provides for stability.
Commander Douglas Mayer is traveling between its outriggers, also known as armors.
We've got over 200 feet worth of armor tunnel here, where as the ship transits through the water at high speed, you get the very slender main body hull, and you have this armor that's cutting the water and maintaining the ship's stability at 40 plus knots. Any other ship in the Navy, you're not going to be underneath the main hull form of the ship like this. This is a one-of-a-kind design.
Pioneering engineering has produced a truly adaptable craft. But patrolling the world's coastal waters requires another genius innovation from the past.
Whoa! The RAF needed a way of knowing if an attack was imminent so they could get their own fighters into the air. This was a huge problem.
To produce more impossible engineering. In its home port of San Diego lies the US Navy's fastest ever fleet. Engineered for coastal missions, both the Freedom and Independence littoral combat ships are changing the face of nautical design.
The littoral combat ships are at the cutting edge of naval technology that allow us to operate at high speeds in shallow waters with stability unmatched by any other naval ship of this size.
As the USS Montgomery powers out to patrol the Californian coast, Commander Mark Stefanik is at the helm of one of the world's most advanced vessels.
Oh, he is definitely cutting the channel. Let's give him 5 short.
But in these busy waters, unforeseen hazards are around every corner.
Got a jet ski off our port side, 350 heading forward aft.
All right, I think we have a good shot at taking them down our starboard side. All right, steady she goes.
Steady she goes, 178.
So there's a number of sailboats that we had to maneuver for, as well as some other small craft. So that did add to the complexity of the ship trying to get underway.
Commander of sister ship the USS Independence, Douglas Mayer, is also well aware these crowded coastal seas can create a navigational nightmare.
Out in the open ocean, it's pretty easy to determine what kind of traffic you're going to deal with because there's very little of it. When you're in the littoral environment, you're operating in the vicinity of very dense commercial traffic.
And in more hostile regions, getting a clear picture quickly is crucial.
Nothing is more critical to the captain, the decision to either engage or not engage a potential adversary.
So how do you identify friend or foe in a split second in some of the world's busiest seas? Achieving this requires another of history's inspired innovations. Engineer Luke Bisbee is high above the British coastline in an iconic biplane, the Tiger Moth, discovering the secrets behind an ingenious piece of wartime engineering.
This is really incredible. What an amazing view. What an amazing airplane. In the mid-1930s, around the time that this aircraft was being used to train RAF pilots, the skies around the south coast of Britain were actually a fairly empty place. But with another war looming on the horizon, the Air Ministry was facing a serious problem.
Long-range Zeppelin bombers had terrorized London during the First World War, and the nation's air defenses had struggled to cope with the German attack.
Since that time, aircraft engineering had advanced greatly, and and they can now fly higher and faster, and this meant they were outside the range of anti-aircraft fire. To stand any chance of successfully defending the country, the RAF needed a way of knowing if an attack was imminent so they could get their own fighters into the air. This was a huge problem. Finding a solution required some ingenious thinking.
The solution would come from Scottish physicist Robert Watson Watt. Working as a meteorologist during the First World War, Watt had detected the signals emitted from lightning by bouncing radio waves off storm formations.
And in 1935, with another war looking increasingly likely, he theorized that rather than bouncing radio waves off of thunderstorms, he could use them to detect incoming aircraft. He named his invention radio detection and ranging, eventually shortened to radar, and it dramatically changed the outcome of the Second World War. This is how Watt's system worked. In front of me, I have a slinky, which is stretched out between me and a potential incoming aircraft. And to work out the position of that incoming aircraft, a radio wave will be sent out into the sky, and I can simulate that by shaking this slinky. So you can see that when I send out a radio wave and it hits the aircraft, it gets reflected back. And this is precisely the principle that Watt was relying on. I send out a series of radio waves, it hits potential incoming aircraft, the signal gets reflected back to me, and I can detect the aircraft's presence. Because we know that radio waves travel at the speed of light, by working out the time difference between the time that a signal is sent out and the time that it comes back, I can determine how far away an aircraft is. And this was something that had never been done before.
In 1935, Watt successfully demonstrated his system to the Air Ministry. And by 1938, the first 5 radar stations covering the approaches into London became operational.
The system was codenamed Chain Home, and it relied on huge masts like this one to send radio waves out into the sky.
By the outbreak of war, a network of 21 steel transmitters and wooden receivers were constructed along the southern and eastern coasts of the UK.
All right. Oh, that is a pretty amazing view. The Chain Home system was the first application of a radar air defense system anywhere in the world, and it gave the British a vital edge over the Germans.
It was so powerful, it could detect a German formation over 150 miles away.
And in 1939, the Chain Home Low system was added, which allowed observers to detect not only distance, but also height. And this is a really incredible piece of engineering.
"80 years on, the Littoral combat ships are tackling the world's challenging coastal environments.
Captain's on the bridge.
Carry on.
And crews aboard the Independence variant have the next generation of Watt's engineering genius at their disposal. The Sea Giraffe radar.
Given that this ship operates in the littoral environment, we need a radar that kind of packs a big radar punch, but in a small package. And that's what we get with the Sea Giraffe radar.
In congested, potentially hostile waters, this state-of-the-art system is the key to keeping the multi-million-dollar USS Independence safe.
Once we get here, we've got our critical points in for contacting harbor control.
Okay. There could be potentially several different small craft coming in up to 40 or 50 knots at the ship. You need to have that capability. Where there's a lot of ambiguity between the good guys, the bad guys, and the in-betweens.
Sea Giraffe can detect 200 air and up to 400 seaborne targets simultaneously. Simplifying a complex picture, its advanced technology analyzes critical characteristics such as altitude and speed, deciphering a threat level within seconds.
Its ability to provide a very clear picture to the operator is what makes it special. We can separate the wheat from the chaff on a radar picture much better than a traditional radar would.
And despite its impressive capabilities, this advanced radar system is significantly smaller and lighter than a typical destroyer's.
It all is in keeping with our desire to maintain speed and agility, and it's a perfect fit for LCS.
The Littoral combat ship fleet navigates parts of the planet the US Navy once thought impossible.
I feel like we're doing something that we haven't done before. I truly think that this is pushing the boundaries.
And its inspired engineering will continue to open up new horizons.
The opportunity going forward is limitless with what we can do with these ships. I'm just so extremely excited for the crew that's going to get the opportunity to sail in this ship and take her around the world.
By learning from the pioneers of the past.
Yes!
Upscaling and developing innovations of their own, engineers have written a new chapter in nautical design and made the impossible possible.
She's basically one of a kind as far as warship goes. I am sailing a ship that's unprecedented. You can't find another ship in naval history that's able to achieve similar features as the Littoral combat ship.